Welcome to this part 2 of this advanced reinforced concrete design course. We are discussing columns. In this part of the video, we are going to discuss about the code provision that exists in IS 456, and also we'll discuss the behavior of short RC columns under axial, pure axial compression. Right. So after watching this video, the student is expected to learn about the limits of slenderness ratio that are specified in the IS code, and also what are the minimum eccentricities that need to be considered in design. Then he or she should be able to understand the code requirements on what is the minimum longitudinal reinforcement requirement and what is the spacing between them. So the detailing aspects, we will talk about it. And then we will also see how the code procedure it can be used to calculate the axial compression capacity of a concentrically loaded column. And also the student should be able to distinguish the difference in behavior between a column that is having transverse reinforcement as ties, or with spiral reinforcement as a transverse reinforcement. So we'll discuss what is the change in confinement behavior that happens, and then we would also talk about the effect of confinement on the axial compression behavior. All right. So IS 456 gives you limits for slenderness. The reason is, as the column becomes more and more slender, we need to consider the additional bending moment also that comes into effect. That we will discuss that in a separate part. And also the code prevents the designer from designing a column that can undergo buckling failure. So it specifies some limit. So you can see class 25.31 that specifies that the ratio of the unsupported length to the least lateral dimension of the column should not exceed 60. So the maximum value for a typical column, the L by D ratio. Here it is unsupported length. We also discussed in the last part of the video how the unsupported length can be calculated, and the least lateral dimension ratio cannot exceed more than 60. So by having this provision, the code is indirectly prohibiting the design engineer from designing a column to fail in buckling mode. And if you have a cantilever column in any given plane, then the code again specifies that the the unsupported length should be kept less than or equal to 100 d square by d. For example, if you take a square column of, let's say, 400 mm by 400 mm, then your L by B ratio should be less than equal to 100. So the code is giving you slightly a higher uh, slenderness limit for a cantilever column. They are not very common. If at all we are designing, and also the axial compression load is expected to be less, so that is the reason the code is slightly giving a higher value. Okay, so these are slenderness limits. Now let us see, though we are talking about pure axial compression, columns are never subjected to only pure axial compression. They will always have some bending moment. So why is that we need to consider? That how do you consider the effect of this bending moment is by considering minimum eccentricities that are going to come in the load transfer. So why is that we need to consider minimum eccentricities in design? Because the latter loads, sometimes if it is not considered in design, though the designer may think that only the loads are getting transferred as an axial compression, but in practice you will always have some eccentricities of load transfer, so that have to be considered. In addition to that, so because of that, some additional bending moment will come. And second reason is the if the ratios of live load to dead load are high, then your live load placement also will play an important role. So the live load patterns have to be considered in demand estimations. So if live load placements are not considered in design, then again it will lead to some bending moment, additional bending moments. So that to account for that, the code is saying that you need to consider some minimum level of eccentricity in your design. And most of the time you will have some accidental lateral or eccentric loads, because though we assume that the structure will be used in a particular way, there may be temporarily the loads, heavy loads may be kept which is eccentric to the column. So that may lead to some bending moment. So you may have accidental lateral and eccentric load that has to be somewhat accounted in the design process. The most important thing is you will always will have errors in construction such as misalignments. The column may not be straight, so you will have initial imperfections in the constructions. That will again will induce some bending moment that we need to consider in our design. And sometimes the design engineers may underestimate the effect of slenderness. Okay, because again slenderness we have discussed in the previous parts of the module. It is purely a function of your effective length, and again the effective length depends upon what kind of boundary conditions that you have, right? And also whether the column is part of the sway frame or non-sway frame, which we have discussed in depth. So if you are not careful in estimating correctly that effective length, then your bending moments may be underestimated. That also could to tackle that, the code is saying that you need to at least consider some minimum eccentricities in your design. Now let's see what are the values for this minimum eccentricities. So class 25.4 of IS 456 2000, it gives you some minimum eccentricity. So last class or last part of the video we have discussed this. If you're taking a column, right? So you can have bending about both the axes like this. So the major axis dimensions we consider that as dx, the minor axis dimension we consider that as dy. So you see that what are the minimum eccentricity that code. If I'm talking about, let's say, the x-axis, and let's say this is y-axis. So what are the code says? The ex minimum that need to be considered is L by 500 plus dx by 30, right? So for example, let's say if I take a column of L is equal to say 3003 meters or 3000 millimeter, and a D of let's say 400, then you say, if you see the minimum eccentricity should be 3000 by 500 plus 400 by 30 should be the minimum eccentricity, or 20 mm, whichever is greater. If this value works out to be less than 20 mm, then you should not take that as the minimum eccentricity. You should take 20 mm as the minimum eccentricity should be considered. So whatever the PU that you are doing, then you should also consider mu in your design, that is equal to PU multiplied by E minimum. So that is a concept. So always the code wants you to design for some minimum bending moment about both axes. Now similarly, EY minimum also we need to consider, that is taken here as L by 500 plus dy by 30. So in this case, you're going to talk about what are the minimum eccentricities for bending about y axis will be PU times EY minimum. Then EY minimum is given here. So in both the axes, the minimum eccentricity about x and y, we need at least to take 20 mm. But if this value comes out to be higher than 20 mm, then we need to take that value for calculating the bending moment to be used in your design. Right. If it is a non-rectangular or non-circular cross-section shapes, then E minimum is taken as LE by 300 or 20 mm, whichever is greater. Okay, this is for non-rectangular and non-circular cross-sectional shapes. You take this. You have a hexagonal or polygonal shape column, then you calculate your effective length and use it for your minimum eccentricities to be used in your design. So that's what the code says. Right. Now let's see what are the core requirements for reinforcement, minimum reinforcement and detailing. And you can see the longitudinal reinforcement, the code is saying that minimum of longitudinal reinforcement should be at least 0.8 percentage of your gross cross section area. So again, if I'm taking a column of 400 mm by 400 mm, then this will be your AG. So I need to put at least 0.08 times 400 multiplied by 400. That should be the minimum amount of longitudinal reinforcement that we need to put in the column. And this, in my opinion, I think we should put at least 1% per column. Okay, 0.8 is slightly on the lower value. So I would say 1% is a good practical number that we need to put in your columns. Now, for example, sometimes for architectural reasons, for aesthetic purposes, if you are keeping a larger column, then the minimum reinforcement can be lowered because it is just not taking a major load, but the architect wants it for aesthetic reasons. In such cases, the minimum area can be taken as 0.8 percentage of AG that is required to resist direct stress. That means whatever that axial compression bending moment that you're getting from your analysis, you calculate your the cross section area that is required to resist that stress. Then that area you consider in your calculations of your minimum reinforcement requirement. Right. So now let's see for pedestals. Pedestals again we discussed. Pedestals are stub columns where your L by D ratio is less than 3 and they're predominantly compression members. The bending would be very less. So they can be designed as plain concrete column as well, because again we have discussed the compression resistance comes majorly from concrete, and the bending resistance in a column majorly comes from your longitudinal reinforcement. So, but that's why the code is saying that it is reduce the minimum reinforcement ratio. It is saying that okay, if a pedestal, it's not really a bending dominant behavior, it is going to be predominantly under compression. So you can reduce the minimum reinforcement ratio to 0.15%. So that means 0.15 times your gross area as your longitudinal reinforcement requirement. Walls, again, reinforced concrete walls can be load bearing or shear walls. I think we will talk about shear wall in the coming part of the module. In RC walls, again, they are compression members. So the minimum, because they're thin members, the code saying that minimum we should have at least 0.15% of your gross area, and it can be reduced to 0.12% if welded wire mesh is used. You can also have these kind of welded wire mesh that are readily that is available, okay, at a certain spacing, and they will be you can get them in the particular gauge thickness that if you're using, again the area has been reduced to 0.12%. Okay, these are the minimum reinforcement that need to be provided. Again, because why the minimum reinforcement has to be provided to take care of the bending resistance. At least the sections or elements should have minimum bending resistance. That is why the code is mandating you to have some minimum longitudinal reinforcement. Now, maximum reinforcement. So let us see now what is the maximum reinforcement. Maximum reinforcement is actually coming mainly from construction point of view. Usually columns we don't provide more than 4% of your cross section area. So actually this is the recommended value. However, the code is allowing up to 6%, but if you put 6%, the concreting will become very difficult. So it is not a good practice. So I would say limit of 4% of the cross section area can be considered as the maximum reinforcement for longitudinal bars. Now, again, minimum diameter and number of bars also we need to consider. And you can see that longitudinal bars can undergo buckling, which we will discuss in the coming parts of the module. And if you see here in both columns and pedestals, we should not have longitudinal bars less than 12 mm in diameter. If you're using 8 mm or 6 mm, then your bar can undergo some buckling. So that we need to be careful. So that is why the code is saying that minimum we should use 12 mm bar as a longitudinal bar, and also the spacing between them cannot be too far. So you see here they cannot, the spacing between the longitudinal bar cannot be more than 300 mm. Okay, so this is also to make sure that you have a nice distribution of longitudinal bar, because columns again will have bending moment about both the axes. So the code is saying that you need to have a nice distribution of longitudinal bars, which has to be at least spaced not more than 300 mm apart. Now we need to also at the same time careful. We need to have the spacing between them, between the longitudinal bars should not be too close also. This is again mainly coming from the requirement. Let's say if I'm using a normal strength concrete with aggregate size of let's say 20 mm or so, then the size of the aggregate itself is 20 mm. So when we do concreting, we need to have a the aggregate should pass through the steel cage, and so that you don't get segregation and honeycombing issues. So that is the reason the code is saying that the clear distance between the bars like this from here to here, this is SC, which is a clear spacing. It cannot be less than it cannot be less than 1.5 times. Let's say if I'm using 25 mm bar, so 1.5 times 25 mm or 40 mm, whichever is larger. So that means let's say this 1.5 times 25 is 37.5 or 30. So I need to make sure that at least the spacing between the longitudinal bar should be 40 mm. In my opinion, the spacing between the longitudinal bar should be at least 3 times the size of the maximum aggregate that you're using. So if I'm using, let's say, 20 aggregate in my concrete maximum size, at least the space between the longitudinal bar should be 3 times 20, which should be 60 That's a good. This will ensure that the concrete can flow among the reinforcing bars. Right. Now let us see what are the cover to reinforcement. Again, from durability point of view, in the durability chapter, we discussed in depth what are the minimum clear cover requirements. Is one of the most important requirement that the cover has to be minimum so that the durability is ensured. So again, for columns are very important members, we need to have a minimum clear cover of 40 or bar diameter, whichever is greater. So if I'm using, but generally we don't use more than 40 diameter. But if you're looking at a very massive column, sometimes specially ordered bars can also be used. In that case, a minimum clear cover should be higher. But 40 is a good number. That is the minimum clear cover to the ties. Okay, so that is what the code is saying to the column ties is recommended to the code for columns in general. And now, if my column size is very small for some reasons, okay, let's say if I'm using 200 300 size columns, or let's say the diameter, the depth is, or size is less than or equal to 200 then if I'm also using the bars which are not more than 12 then the code is saying that you can reduce, because for a small size member, if I'm putting larger cover, then my bending moment resistance will come down. So the code is relaxing this requirement, and if I'm using a small size columns, then I'm permitted to have a reduced clear cover, because if I'm again putting 40 the efficiency of bending resistance will come down. So that is the reason code is allowing you to have a slightly reduced clear cover of 25 And if I'm using walls are usually 200, 250, in fact, sometimes it will be 150 also. So you have a minimum clear cover of 15 or bar diameter. If I'm using say 12 then whichever is greater. So minimum of 15 is generally recommended as a clear cover for walls. Okay. And again, usually, even for small 2, 3, 4 story buildings, then your minimum thickness of the wall should not also be less than 125. So if I'm using, let's say, 125 thickness walls, then I cannot have a large cover. Then your bending resistance again will come down. So that is the reason the code is saying that you need to have a clear cover of 15 So now let's talk about what are the requirements for your transverse reinforcement. So those provisions are given in class 26.532 of your code, where you have tie diameter is given. Tie diameter is what? Transverse reinforcement, or also called as ties in a square or rectangular columns. And minimum you should use 6 And if I'm say, let's say maximum longitudinal size that I'm using, let's say for example 32 then 32 by 4 is 8 So in that case, the tie diameter has to be at least 8 In my opinion, at least you should not use less tie diameter. You should use at least 8 ties in your columns. Again, spacing for the ties. So if I'm looking at the column, let's say these are your longitudinal bars, right? And then you have ties like this, which you will see in the. So basically, what the code is saying is this diameter has to be greater than maximum longitudinal bar diameter divided by 4 or 6 Generally, 8 is good. And also, you need to have the spacing between the ties should satisfy this requirement. It should be less than or equal to the least lateral dimension of the column, 300 or 16 times the minimum longitudinal bar that is using. So let's say I'm using 16 and 20 longitudinal bar in your column, then this will become 16 times 16 will be your spacing. And let's say if that column size is 400 then it should be 400 here. If I'm using 16 as a minimum longitudinal bar, 16 times 16 and 300. So you will find that it should be less than or equal to one of this requirement. So you have to provide the least of that. So this would control your spacing. Right. So then in this case, this will become your tie spacing. And then for spiral columns, the pitch in spiral columns, we don't talk in terms of spacing. We call the spacing of the spiral is called as pitch. That pitch has to be less than or equal to 75 or the core diameter by 6. Now let's see what is the core diameter. Core diameter is usually the distance between the center line of the tie to the center line of the tie. Outer to outer, between the center line, definitely we consider them as a core diameter. So the pitch has to be, let's say if you have a core diameter of 300 mm, so then you have 300 by 6, which is going to be 50 mm. In this case, 75. So you have to take the least, which is 50 mm. So pitch has to be at least provided with this kind of spacing. And also you need to have this is for pitch, so this is also should be greater than, at least this is also minimum, it should be greater. Again, if the spacing between the spiral bars are less, then again aggregate cannot go through. So that is the reason the code is saying the spacing also should be greater than 25 mm or 3 times the diameter of the spiral, or the transverse reinforcement, that what I'm using, which is, let's say if it is 8 mm, then it will become 24. Okay, so you have to have some, satisfy some, you should not put spacing too close, and also it should not be too high. The maximum spacing is controlled to make sure that your longitudinal bars are not going to have a premature buckling, but the spacing, the minimum spacing or the spacing between the ties are kept at a certain value so that the aggregate can basically go through the concrete. And so the code also gives you some detailing, other detailing requirements. Let's see what are the detailing requirements that are given in the code. For example, what we are seeing here is a rectangular column. You find that the maximum spacing between these longitudinal bars should be less than or equal to 300 mm, like what we have discussed. And again, the clear cover to the link should be greater than or equal to 40 mm. That also again we have discussed. And then we need to have, actually, if you have a very long column, it's better to put this kind of a two closed ties. So this is one closed tie, this is another closed tie. So this is one and this is another. So this kind of closed ties you can put. And then again for circus, the square column with the spiral reinforcement also, the requirements again we have discussed that the clear cover to the link should be at least greater than or equal to 40 millimeter. So again, if you look at the next spacing, again you can have longitudinal bars that are not restrained by the ties, but however that spacing should be less than or equal to 75 mm. For example, this bar is restrained by the tie, and this bar is not restrained by the tie. So the spacing between the bar that is restrained, longitudinal bar that is restrained by the tie, and the one that is not restrained in both the directions should be less than or equal to 75 mm. Again, the longitudinal bar also can buckle in both the directions. So the code is making sure that to prevent that, you have this again 75. So you don't have, all the bars need not have be restrained by the tie. So you can have one bar that is need not, in this location you need not have this tie. So that is what the code is saying. But if you don't need to provide this tie, then the spacing between this corner and this intermediate bar has to be less than or equal to 75 millimeter, right? So in this case again, if the maximum spacing between the outer to outer longitudinal bar is less than or equal to 48 times your tie diameter, then you can have the intermediate longitudinal bars can be restrained by an open tie. So what is the difference between a closed tie and open tie? Closed tie should have like this, right? And then it should be as a single piece, and then it should go and have this 135-degree bend. So this is a closed tie. You can also have this kind of open tie in some certain situations when the outer to outer distance between the farther longitudinal bars is less than or equal to 48 times your diameter of your tie, then the intermediate longitudinal bar can be restrained only by a open tie. So it is basically helping to ease the construction. Similarly, for example, if you have a L-shaped column like this, again we need to make sure that all the longitudinal bars are adequately restrained by the tie. Okay, so in this case, then what we can do? So we can put like this. So basically here, if you look at it, you have, this is your tie that is going. So this is one tie that we have on this side. Then you have another tie for this side. So it is all the bars are nicely restrained. Similarly, for the horizontal direction, you have, this is your one tie, and the next one is this. So you can see here that all the longitudinal bars are nicely restrained by the tie. So if you have multiple of these ties, intermittent ties, it also helps in confining the concrete core really well. So that helps to improve the performance and improve the ductility. So that is the reason the code is making sure that all the longitudinal bars are adequately restrained by this ties. So only thing is, if the spacing between the farthest longitudinal bar is less than or equal to 48 times your tie diameter, then the intermittent longitudinal bars can have only open ties. Sometimes if the longitudinal bar requirements are very huge, then what we also do is we put this kind of a bundling of this kind of a longitudinal bar like this. Then if you are doing like this, because always what we want these longitudinal bars to be as far as away from your CG of the cross section, so that you get the maximum stress on the longitudinal bar that will help me in bending resistance. In that case, if I'm not able to put all the bar at corner, then what we can do is we can put this kind of create a small column inside the column, but these has to be restrained by a tie like this. Okay, so these restraint has to be done. And again, when you look at this and this spacing again should not be more than 300 mm. So this kind of a one, you can have one closed common tie. In addition to that, the corner four longitudinal bars can also have a separate tie. So this way you make sure that you have better confinement, and also the longitudinal bars are not going to buckle in a. Now let us see how the nominal capacity and is calculated for the concentric axial load. Okay, so now if you remember in the materials chapter, so we discussed the stress strain curve for concrete. Okay, this is for concrete, right? And this is for steel. So if you look at it, this is the design stress strain curve that we are going to use, right? For pure axial compression. So if you remember, for pure bending, what are the epsilon Cu that we considered? We considered that failure strain as concrete as 0.0035. Because bending is not a very brittle mode of failure, so the code is asking us to take a slightly higher value of 0.0035 in our design. However, compression, which we have seen when concrete fails in compression, is a very brittle mode of failure. For pure axial compression, epsilon Cu is limited to 0.002. So code is asking you to take a very small strain than what we have considered for bending, and the failure strain for pure compression is taken as 0.002. And so basically when this strain it reaches, that is your failure condition. So at this strain of 0.002, now what is the stress in concrete as per our design stress strain curve? It is 0.447 FCK. FCK is your characteristic strength, and we are using about 44.7% of your characteristic compression. That is the maximum stress that concrete can offer as per the IS code. Okay, when the strain is 0.002. So again, for a column, we know that if you look at the section, again, we have longitudinal bar, right? And in addition, you have a tie like this, right? So let's say this is the total area. Let's say this is B and H. So AG will become B into H, and these are your longitudinal bars, right? So we have discussed in the axial behavior, concrete and steel are going to act like two springs in parallel, and then you are going to have a strain compatibility, and both of them will contribute to load resistance. Now, if I'm taking 0.002 as my failure strain, so what is the stress that is offered? It is 0.447 FCK as per your IS code, that I'm multiplying by the gross area. Of course, if only the concrete area we need to take, so I'm taking gross area here, and then I will subtract whatever the area that is occupied by the steel. So you see here, this is your concrete contribution. Your concrete contribution. Now this is your steel contribution. So now steel contributions, when you are taking failure strain as 0.002. Now, what is your stress in the steel? So, if you see here, this is your 0.002, and this is your stress strain curve that what we have taken. So, if you look at it here, so you take this is your value, so that is your 0.746 Fi. So, this design stress strain curve, what is that we have taken? We have taken this for Fe 500. Similarly, you can have design your design stress strain curve for Fe415 and Fe250 is also given in the code. But this curve, whatever that I'm showing here in the slide, is valid for Fe500. So for Fe500, for a strain equal to 0.002, what is the stress that as per the IS code design stress strain curve, I'm getting 0.746 Fi, right? So if I write this in a generic sense for any grade of steel, then this is nothing but stress in the steel, okay, steel stress minus this 0.447 SCK. Why is that we are doing? Because I have to subtract the area of the steel that is from this concrete contribution. So that is the reason. Now, what is the stress that concrete is contributing? 0.447. So that FSC minus 0.447 FCK, when I subtract it, it automatically takes care of the additional area that I have considered here, which is basically I need to take only AC. But here I have simplified and I am taking AG. So what is AG? AG again can be written as AC plus AS. So now I have to subtract this AS. So AC will be AG minus AS, which is equal to AC. So that is what I'm doing. So this stress, if I'm subtracting it, so this will become your steel contribution. So this is your steel contribution, right? So again, this is what is that we have done. So we are doing this calculation corresponding to failure strain of, this is being done for a failure strain of point not 2, because that is the failure strain for axial compression that is specified by the code, right? So let's say, right? So again, the definitions for this things are given here. Ag is the gross area for a column of B and H. It is B times H. ASC is your area of your longitudinal steel. Now the steel can be in compression or tension. In this case, we know it is pure compression, so all the reinforcement is going to be in compression. So this is basically area of your longitudinal steel. And FCK is your concrete compressive strength, characteristic strength, and FSC is the stress in steel corresponding to a strain of 0.00. So this is a generic thing. So if you go back and look at your design stress strain curve for Fe500, we have just looked at it. It is equal to 0.746 Fi. But if you look at Fe415, it is going to be 0.790 Fi, and for Fe250, it is going to be 0.87 Fi. Okay. So and we know that Fe250, what is the yield strain? If you divide basically 250 by 200 into 10 to the power 5, it works out to be 0.00125 will be your yield strain. And that is the reason the code, you divide that and then you get your yield stress. That's why for a strain of 0.002, Fe250 reaches its maximum stress what it can offer, which is 0.87 Fi. But nowadays, we don't use Fe250 rebars. We are using actually mostly Fe500 or Fe550 in our construction. So this would become more relevant. Okay. Okay. In addition to that, we have discussed that code requires that all the columns to be designed for minimum eccentricities in loading. Okay, that also we have to take it. So this is for pure compression. Okay, so pure compression, what are the capacity that I can use for calculating, right? And we have seen. So again, this equation is derived for a failure strain condition of 0.02. Now, so the code is saying that, okay, this is the expression that is valid for pure compression. And now the code is saying that let's simplify the formula, and it wants to reduce this PU naught naught by approximately 10 percentage. And if it's just, because this we got it for FE 415. So when the code was written in 2000, at that time 415 grade steel was more common. So what they've taken was PU naught naught for Fe 415 is 0.447 FCK plus 0.79 Fi minus 0.447 FCK times your ASC. So that is the reason. This again, why is this 0.79 Fi for Fe 415 for epsilon S equal to 0.002 strain, you get the stress. Okay, so this is the expression, and code is proposing the simplified formula. So then what saying? So this is actually, this equation is valid for all grades of steel, but we know that this stress is going to change depending upon the grade of steel. But code is saying, okay, let me knock this by about 10 percentage. If I reduce this by 10 percentage means if I multiply by 0.9, then you get pure simplified pure compression formula as 0.4 FCKAG plus 0.79 multiplied by zero point 0.9 will give you 0.67. Again, 0.447 multiplied by zero point 0.9 will give you 0.4 FCK. So this is the way that we got this simplified expression for your pure compression capacity. And so this is the pure compression capacity specified by the code for all grades of steel. So only thing is the Fi will change depending upon the grade of steel. Similarly, if you know the concrete strength, you can plug in that value and you can get your pure compression capacity. So the actual equation is this. Why is again code is reducing it by 10%. Again, why? Pure compression, when it is failing, it's a very brittle mode of failure. So you want to estimate that capacity slightly conservatively. And again, we discussed that there is no such thing like pure compression the column will be subjected to. There will always be some level of eccentricity. Again, to account for that, the code is reducing this by 10%. So that is why we are multiplying the actual equation by zero point 0.9 to end up with this final equation. Now, for spirally reinforced columns or the column that are confined with spiral reinforcement as ties, code permits the load capacity to be enhanced by 5%. Okay, again, we talked about two types of reinforcement. You can have longitudinal reinforcement confined by individual ties or transverse reinforcement, or you can also have a spiral, which is a continuous reinforcement. So if I'm using spiral reinforcement as a transverse reinforcement, then the code is permitting that this capacity can be increased by about 5%. So we'll talk about why that the code is saying.